Um, we'll start in a few more minutes. Can anyone confirm if I'm audible in the chat? So this class is replacement for week four. Week four actually we didn't have last time. This would be used to discuss on week four's lecture. And tomorrow again, as usual timing on Sunday, we will have our week five lecture as planned, and next week again week six on Sunday. It's again 3 to 5. So uh, that's the timings that we are still waiting for a few more people to join in. In the meantime, if you have any questions or anything, please type in or share. Hello everyone. I think there is a network issue. I hope am I audible right now? Please type in if you're able to hear me. So we will start on the session today. So this is week four session on NPTEL's Python course, and we did this session today because last time we couldn't work on the session like as the scheduled timing due to a health issue. So as a replacement, I'm actually covering this in today's class. We would anyways be covering on week five from tomorrow. As usual, timings is 3 to 5. and that's our the proposed plan that we are having. So I'm sharing my screen. Please let me know once you're able to see. We're still waiting for a few more people to join, but in the meantime, if you have any questions from last time or any three problems that we wanted to discuss, feel free to share them. Um, so we'll discuss week four, which is on some of the sorting algorithms, which was discussed as part of the lecture series. And we will probably also look at the corresponding assignments, problems to solve during this time. Week three, I think we have discussed about several things like in list, and also solved two column sheets on week three. Um, that was our sort of what we had discussed from last time. This one. Okay, so that's was our discussion from last time about lists, and also we discussed about uh, uh, some initial search binary search algorithm also from last time, which wasn't covered in the last 2 weeks. Also, we solved some problems about binary search. So there was a question in the chat. I think Somojit had a question that if you can discuss some exam-oriented problems. Right. So we will be discussing exam-oriented problems in terms of the problem sheets and assignments, as well as going through some of the topics like sort of like online quizzes kind of thing, which I had shared some resources sometime back. So one resource is like Hacker Lang, where you can solve such problems. And the problems pretty much resemble the problems that you would get in your actual exams also. There are other resources also which I have shared where you can practice more problems outside of the NPTEL problem sheets. But I would say like problem sheets and assignments are one of the main sort of things that you should practice from because they have a very comprehensive list of assignments that gives you some idea about the different structures, like how the questions would look like in the exams. So we discussed, then discussed week four, I think, on list some of the quizzes from week four. We'll discuss that today. So if you have any doubts there, feel free to share those in the chat. And we will also discuss some of the problems on sorting also, because week four is mainly on sorting, the most sort, selection sort, insertion sort, and all. I will do some analysis and some problems, like some coding problems, as well as some like problems in terms of like the not only restricting to Python itself, but also to the algorithm also, like in terms of time complexity of different sorting algorithms and all, worst case time complexity and all this. We will discuss it. And some solve some questions on that. So we'll discuss with the first thing, which is I think yeah. So week four, I'm just going to. So we'll first discuss on quick sort. And so to give you a brief, like if you have already gone through the lecture series, I think that would be helpful. But again, for just as a quick reminder, sort of what quick sort is. So I'll go through a Python code, just to sort of give you a hint about quick sort, and probably like give you some aspects of like time complexity analysis and all. So what quick sort time complexity looks like, and how you can improve it better. So those are some of the problems we will discuss. So basically, quicksort is so when we discuss sorting algorithms, we broadly classify them into comparison-based algorithms. Because why is it called comparison? Because we are having to do we are comparing against elements in the array itself. So that's why it's a comparison-based sort. There are other algorithms also, which does a hybrid of comparison and other techniques, like examples like bucket sort and all. We will obviously won't be discussing those topics in this lecture discussions, but if you are interested, I would highly suggest to read through this book, famous book on algorithms called PLRS, which has all such deep details about these algorithms like bucket sort and other kind of sorting algorithms. So that would be a good point to sort of look into. So we'll first look at the Quicksort algorithm, like brief description of Quicksort algorithm and what is it, and then in Python also like how you can sort of like this. So okay, um, there's a question I think in the chat. So can you please revise with code? Yeah. So we today we'll be revising with code topics only to programming examples. In terms of like so week 4 topics are majorly merge sort, quicksort, and also I think some on tuples dictionaries, function definitions, and list comprehension. So we first cover merge sort, quicksort, and then we'll go to tuples and dictionaries and definitions, and then we'll do so with sort of examples to code it out and sort of motivate the team. And also the discussion would be also to formulate some what sort of questions can be asked in this setting, like what like popular questions people in the exams are mostly asked. So those kind of things we will also do work on. So just give me a time. Just trying to open my share my screen. Okay. So once you're able to see my screen, let me know. So we'll discuss Mozart and Quicksort both together. Sort of. I think that would like give you some aspects of the understanding of both of them. So let me share my screen and let me know if you're able to see my screen. I'm now sharing. Yeah, just let me know if you are not able to see my screen. I'll sort of reshare it. It's not visible. Um, okay. Um, okay, so we'll discuss merge and quicksort both. So basically, sorting algorithms, as you know, like we discussed last time, insertion sort, where this kind of algorithms have worst case quadratic performance. Like if you, for example, if you have n number of elements in the array, then your performance worst case performance would be something around or order of n square. So typical examples are like insertion sort, selection sort, double sort. They have all the quadratic worst case performance out of n square. Now, what are like some of the faster sort of like comparison based algorithm look like? So, like the best we can do is order of n log n, which is much more faster than order of n square. And obviously, if you know about, if you have previously studied through time complexity analysis and all, you probably would know why this is. But again, I'm giving you a brief overview. So the function login is much sort of it's much it's lower if you plot log n versus n. So let's say y equal to x and y equal to log x. X is increasing at a much higher rate than log x because log x is sort of it's diminishing, but it's still an increasing function, but it's the rate at which it's increasing is much less than y equal to x. So order of n log n is still much more has a much less rate of increase than order of n square. So in typical sorting algorithms, we want to have faster comparison based methods, and merge sort and quick sort, both of them give us complexity of order of n level. So this is a very important question. I think mostly in major exams, competitive exams, this question gets asked a lot, like in terms of which sorting algorithms give you n log n as a complexity. Or also, like for example, what is the time versus complexity of quick sort, for example, what is the versus complexity of merge sort? This kind of questions, the answers are the same, just a way of sort of reframing the questions and ask. So this type of questions are very much popular in exams. So just a reminder, and we'll go through why it's coming out to be n log n also. And after that we'll write a program and sort of in Python and sort of work it out and see. So we'll first, let's say, I think let's discuss quick sort. I think after that we can discuss merge sort. Um, okay. So the quicksort algorithm is the following. So given an array of n elements, and we mostly consider elements as integers, but you can also think of array elements as floating numbers also. So that is also one way. But for the timing, we are considering all integers only as main sort of uh, as a main sort of assumption. So now, if array only contains one element, then we just return that element. So because our goal is to sort the array, right? So if the array element contains just one element, we just return that itself. Else, if the array contains more than one element, what we do is we pick any one element as a pivot. Sort of. And what we do is we partition the elements into two subarrays. The elements which are less than or equal to the pivot, we partition into the left subarray. The elements that are greater than the pivot, we partition to the we move it to the right subarray. So basically, we are picking any one particular element as a pivot, and with that pivot, we are dividing the entire array to subportions, left subarray and right subarray. And what we are doing is like all the elements in the original array that are less than the or equal to the pivot, we are pushing it to the left hand side of the subarray, and all the other elements which are greater than the pivot, we are just moving it to the right hand subarray. And what we do now is like we recursively do this thing on the left subarray and on the right subarray. So basically, way of saying that is we do quick sort the two subarrays. Left subarray, we again perform the same thing. We again keep a pivot. We again partition left subarray into two parts, and again do the same thing. Right subarray also we do the same thing. And ultimately, when the algorithm converges, we just return the final results. So we give an example. So let's say we are given an array of integers to sort like this, 40, 20, 10, and so on. So now, let's say there are a number of ways to pick this pivot element. So, like how many elements you have here? So you have you have uh, 9 elements here. So there are 9 ways to choose a pivot in this setting. So let's say I pick the first element in the array, which is 40 as a pivot. Now what I do is given a pivot, I partition the elements as I mentioned to such that one subarray, which is the left hand subarray, or sorry, in this case the right hand subarray, contains all the elements that are greater than pivot, and the another subarray contains elements which is less than pivot. And the subarrays are stored in the original data itself, and the partitioning loops through this entire array, and it swaps the elements below and above the pivot. So since we are doing some kind of swapping operation, because all the elements that are less than pivot, we are swapping that with the original array items. So we are performing a swapping operation. So we do this recursively over time. So we focus to an example. So I think 40 and then what it was 20. So a pivot index is set to 0. and 20, 10, 80, 60, 50, 7, and 30 are the remaining elements around. So all the array elements that are less than 40, I move it to the left hand side of 40. All the elements that are greater than 40, I move it to the right hand side. So what I do is uh, I keep a index which is like two big index and two small index. So what this indices mean is that two big index means that the index of the element in the array which is bigger than 40. That means which is larger than 40. And two small index basically means which is smaller than the same. So here what I'm doing is that while data to big index is less than equal to data pivot, that means when the data to big index is less than equal to pivot value which is 40, I just implement it first and then I assign it. So is I think in C++ this is uh, kind of common to you that you first do a plus plus and then you do assignment. So basically what I'm doing is that I'm two big index. I'm sort of um, I'm first assigning it to the I'm first initializing two big index to the first element in the array, which is after the pivot at index one, and the last element in the array I'm assigning to two small index. What I would do now is like for any of the data that falls below 40, I just keep I just keep as it is. What if I go to the next slide? Sorry, 20, 10, 20, 30, because sorry, 80 it was index 3. So 10, 20 and 10 I keep as it is. At index 3 I have 80. So now what I do is like I see that data too small index is greater than data pivot or not. And if it's I again decrement the index for too small index. So from 8 it goes to 7 to 6 and so on. And so 100 is obviously greater than 40. So I decrement too small index. Now if I see that two big index is less than two small index, that means to be index is at 3 and two small index is at 7, I swap the two elements. So this is what I'm doing. Um, and while two small index is greater than two big index, that means this portion, which is the I just go to the initial step again once more to step number one. So I do this over time, and I will finally sort of have all the elements arranged in uh, two partitions of one is less than 40 and one is greater than 40. So after the partition result, this is my what this thing looks like. All the elements on the right hand side are less than 40. All the elements on the left hand side are greater than 40. 7, 20, 10, 30 are less than 40, 50, 60, 80, and 100 are greater than 40. So this is after I do pivoting and then rearranging the array elements on the left hand partition and the right hand partition. Now I apply recursion. So I think we discussed recursion a few weeks back. I will again discuss this today also, recursion, because function definitions is one of the topics. We will discuss that once more. So in recursion, what it means is basically the first operation that I did here. So the entire partition thing that I did here, entire operation, I repeated once more on the left hand subarray only. And I do the same for the right hand subarray. So that means I again pick a pivot at the first position, which is let's say 7 in our case, and do the swapping operations and all this. And on the right hand side, I pick 50 as the pivot and do the swapping operations on all this. And I continue that in subsequent recursions also, like subsequent subarrays that I create. Um, so so any questions to this one? Like if we could go to the analysis where we get log n as time complexity. So any questions to this one? If you have any questions, feel free to ask. Okay, so we'll go ahead then. Um, so so this is quite easy. I mean, like the it's also quite intuitive because we know like this is how quicksort we are actually sort of picking one element as a pivot and sort of pushing all elements less than equal to that to the right hand side, all elements to the greater than that to the right hand side, because ultimately what we want is a sorted array. That means all the elements in smaller numbers should be on the it should be in ascending order. That means all the elements it should start with smaller elements and progressively go towards larger elements in that. So this is intuitive. So we'll look at the analysis now. And it might be a bit sort of difficult to understand at first the analysis, but but we'll keep it short because just to motivate the algorithm we are discussing mostly this. In exams you might be asked main questions about complexity and all, but it might be also be possible that if you are given a problem where you have to think a bit deeper into, like, let's say quicksort analysis on a special type of array. That means, let's say an array has some special properties like every element in the array is like a even number, let's say, or every element in the array is even number followed by an odd number. So some problems can be thought of on top of this. So those can be, so for those I think um, uh, can be sort of a useful thing to know. So one question was that why to study so many different sorting algorithms? Good question, because there's so many sorting algorithms and it's hard to remember what each of them does and all. The main reason for that is that it's actually so sorting algorithms are used. Different sorting algorithms are used in different use cases. For example, in your file storage, for example, where you have in your desktop, laptop, or any thing that you have in your hard drive, let's say, you always do. You always have a file storage, right? So, uh, so when you sort of want to, let's say, sort of click on a file to retrieve a file. Let's say you want to open up a PDF file for a document or something that you want to read up and all. So basically, how those files are stored, those are mostly in some sorted fashion, but also so that why we wanted that in a sorted fashion, because if it's in a sorted fashion, I can just retrieve it by the index number. So basically, that means like, let's say I want to uh, get a document of let's say of some document on my laptop. I want to read. Let's say I open up and sort of do some work on it. And so when I do that in my computer, I don't know, it doesn't know like which sort of memory partition those documents are in. So all it knows is that it has some specific indices, memory pointers where files are stored. And it can just use that in the index pointers to get retrieve the document for me. So if my files in my actual hard drive or storage is are in some manner of sorted order, then I can quickly pick up the retrieve item. And so things like quick sort, for example, or mod sort, basically in file storage and all, mostly mod sort and all these algorithms are used. So these are useful to because it has a complexity of order of n log n. So you want to have very low latency. For example, let's say you click on a document in your downloads folder. You don't want to wait it for like 5 minutes, 10 minutes until that PDF file opens, right? You want to get it as quick as possible, like 1 second, 2 second latency. So for those reasons, you want to have a higher sorting algorithm, which sorts your files in some memory partitions, and you can just quickly get the files sort of in your thing. Things like insertion sort, for example, insertion sort, obviously, as I mentioned, mod sort and all are mostly used in databases. I think database is one of the most important topics where merge sort and all this merge sort is mainly is used in the insertion sort, for example, is also handy. I think in database concept also in SQL tables, for example, SQL tables and all. Many times you do insertion sort there also because the files how they are handled insertion sorts helps gives a good advantage as compared to other sorting algorithms. So the main motivation behind these different types of sorting algorithms is basically to apply it into different problem settings. One is in, let's say, in your everyday laptop or everyday computer, you have a specific use case of hot sort and quick sort. Similarly, in someone who is working on backend, let's say software backend engineer or something, they probably use mostly insertion sort and other sorting algorithms. So different sorting algorithms have different advantages and also downsides also. So that's the reason why we study all this sort of popular algorithms for sorting, so as to give a broad understanding of what types of sorting algorithms there are and which algorithms are better in specific use cases and which are not. So, in the long run, when you solve industry problems, I think that information comes in handy a lot. You know exactly this for this problem you need to use the sorting algorithms. So yeah, that's the main reason I think we are discussing solving algorithms. And I think an interesting point is that till this date also, I mean, most people know about quicksort, merge sort, bubble sort, insertion sort. There are other algorithms, lesser known algorithms like selection sort, bucket sort also. But to this day, there are many sorting algorithms in theoretical computer science research wise. I mean, like in research paper wise, there are many sorting algorithms. Obviously, it's not part of the syllabus, but if you're interested, you can probably read them up. To this state, the base sorting algorithm is of order n log n, but if you see research papers and all, they are pushing even further, like it's even better than n log n and all. So those are kind of interesting topics from a research point of view, where people also discovered a lot of sorting algorithms and work on them. And the main aim is to apply them in problems like in computer organization, like file storage systems and databases. So that's one of the main motivations. So I hope that gives you a rough idea. So yeah, so we are going back to quicksort analysis, and we'll just briefly discuss this thing. I think just to motivate you and give you a revision of the topic, sort of. So as you um, so yeah, if you have a question, feel free to share in the chat, or you can also raise your hand and speak up. So yeah, so we are assuming that the keys are random. That means they are uniformly distributed. And what is the best case running time that we get to? So as you know, like we are applying recursion. So in recursion, what is happening is that the partition splits the arrays into two subarrays of size. Let's say you take the pivot element at the middle element. So as say if you take the pivot at the middle element, um, uh, so even if you let's say for the time being you don't assume which element you are pivoting. Let's say you are taking a pivot as any element in the array. You partition the split arrays into two subarrays of size n by 2 because it's two equal sizes, and you can do the same for quicksorting each of the subarrays. So what is the depth of the recursion key? What do I mean by depth here? So it's so I'm just going through. So I think the depth thing I can sort of briefly discuss in words. So basically, if you go back to the example here, so 40 is the middle element here, and all the elements to the left are less than 40, all the elements to the right are greater than 40. And I again take a pivot here and do the same thing. And I divide this array into two parts. Left each has two elements, so two elements on the left, uh, left array and two elements in the right array. Again, I do the same on the right hand side of the array also, and so on. So, what do you think the so basically we are building a tree kind of structure. So this is my root of the tree, and after that I divide this array, and again I divide this array, and so on. So if you can imagine this as a tree kind of thing where you are branching out different possibilities. So one branch is for dividing this the entire array into two portions, this array and this array, and another branch now is dividing this left array into two portions of size two each. So I have two branch here, and again for this I have two branch here. So each of the subarrays now have size 2. I can do a division here, I can do a division here, and so on. So this is like a tree with branches. So by depth of recursion, I mean the tree that I'm getting, what is the depth? So basically it turns out that the depth comes out to be order of log n. And it's easier to see when you draw the tree and see for yourself why that is the case. And number of accesses in partition. So basically, what it means is that like uh, when you pivot the element and you try to swap and all, what is the number of comparisons that you are trying to make? So the base case running time is basically a product of these two, like number of accesses in partition and depth of recursion is order of n log n that comes out the sort of the best case. So what is the worst case running time? The worst case running time is the following. Assume that the first element is chosen as a pivot. That's your worst case running time. And also assume that you have an array that is already in sorted position. So 2, 4, 10, 12, 13, 50, 57, 60, 100 are already in sorted position. And I take the pivot as the first. So what is happening is that I took the pivot as the first element. All the elements here are obviously greater than the first pivot element 2. So it's all obviously on the right hand side of the pivot element. So I divide this entire array into two portions. One is empty left array, and the other one is entire right subarray. So the left subarray is actually empty because there is no elements here that is less than 2. All the right subarray has all the elements greater than 2, that is 4, 10, 12, 13, 50, and so on. After that, what I do is like again pivot at 4, and at 4 I see no elements. So because I don't consider 2 anymore because 2 is outside the right subarray, so I only consider all the elements in gray as my sort of right subarray, and I take pivot for 4, and all the elements I find to be greater than 4. There are no elements that are less than 4. So again, I divide that into entire right subarray of 10, 12, 13, 15, 57, 62, and 100. And I repeat this process on. If you see this thing, if you see, visualize the diagram of the tree, it would be parent, a root node, which is root of the tree, which is this entire array. You they are divided into two subarrays. Obviously, the left subarray is empty. So you have a right sub branch of the tree, which goes to 4, 10, 12, 13, 50, 57, 60 to 100. And from that right branch, you again pivot at 4, and you again get a right branch of 10, 12, 13, 50, 57, 60, 100. And you again pivot at 10, and you get 12, 13, 50, 57, and so on as a right branch. And you keep on doing this over and over. So, what do you think the depth of the recursion tree in this case would be? It would be order of n, because the number of branches is basically the number of elements in the array that I'm getting. For 2, I get one branch. For 4, I get one branch, and so on. So that's what. So I'm not going to the analysis for the sort again. So depth of recursion tree would be order of n in this case. A number of access partition is again order of n. So worst case running time is coming into the order of n square. So there is an important question which you might get asked in exams, is that worst case complexity of quicksort versus best case complexity of quicksort. Or maybe some examples like which algorithms are and in worst case, not uh, order of n log n. So you are given four options. Let's say. You have to pick quick sort in this setting. So these are some of the exam problems you can think of, which should be mostly asked. So again, what is the thing we can do here to avoid the worst case? To avoid the worst case, what we do is like pick the median value of three elements from the data array. So you can do data zero. So you can do some improve previous selection on. So I'm not going to the exact details yet because this is again a new sort of topic and all, which is kind of out of syllabus. So I'm not discussing that. So that's our quick sort thing. And if you have any questions, we can pick that up and we can solve some Python problems on our quick sort, and then we can go to merge sort also. So any questions to this one? Um, okay, I'm sharing a course snippet. I hope you would be able to see that. I would ask you to please check that course snippet and share any comments in terms of any doubts if you have or any questions why the code is shared like that. So I'm sharing a screen. Just let me know if you are able to see. So there is an algorithm for quick sort in Python. Um, uh, so uh, so we'll discuss this and analyze this and sort of um, work on some problems on all of this. So let me know if you're able to see. You can take a short 5 minutes break to just to analyze this algorithm. If you have any questions, feel free to formulate them and ask them in the chat. Um, okay, I hope you have gone to the code. We can discuss this code now and sort of work on the details of this code. So I'm opening my Visual Studio Code, where we will be discussing this. Um, just let me know when you're able to see my screen. I'll actually share my sort of. I'll actually like just work on this code only in my Visual Studio code. So if you have any questions there, we can directly work from there. So we'll define. So week four also has topics on function definitions. We will cover that along with this itself. So because we need to define a function around, so we'll discuss that as part of this topic itself. With the so this should cover two topics. I think. So okay, let me know if you're able to see now. Um, yeah, I shared my screen. So this is my sort of quick sort algorithm. So first see like how I'm defining the function. So this is my let me write comments here first. This is my quick sort algorithm. So my function definition starts with a def keyword like this def function name and I give some arguments also. Arguments are basically whatever the function is that you want to use. For example, let's say you want to define a function. Function name. Let's say function is like sine. Uh, let's say sine, cosine, tan, like this. So cos, tan. These are some of the standard trigonometric functions that you can define, for example. And in this case, arguments can be your x, y, z. So x-axis, x value, y-axis, y value, z-axis, z value. You can be having like this. So these are all x, y, z are again all like degree like like inputs to the function. Like for example, sine of x, for let's say cos of y, tan of z. So these are your input to the function. In this case, quicksort, I am taking X as list. So X is basically a list like this. So type of X is basically a list here. And len of X is basically the length of the list. So what I'm doing here is um, I am first checking if the length of the list element is actually equal to 1 or not. So this is a Boolean operator. That means if my again we this is for last few weeks lectures also the Boolean operators and all. So if the length of the list is equal to 1, that means the list has only one element. I just return that list itself x. Else what I do is I also check either this or this. So if len is equal to 1 or len of x is equal to 0, that means my element is this basically means my array is empty. So I'm just writing comments here. This is something we called as base case when I'm defining if else condition. So this is a base case condition. So so with this example, we will see two things. One is function definition, how to define function, how to call a function and all. These are again topics from week five, week four itself, and some portions of week five also. Function definition plus how to call functions, and also we'll see recursion also. Recursion, um, recursion topic and function, which is basically function calling itself. So that's the main idea. So So now I'm defining quicksort. So len of x is equal to 1. All len of x is equal to 0. This is my base case. If it is equal to 1, so that means the first condition it means if the length of x is equal to 1 or 0, I just return the list. So this is my sort of the main idea. The first question is the that says is that so this basically means my list is empty. So one means I have single element and zero means basically an empty element, empty list. I don't have any element in this. So that's the best case. Now I do this thing. I take a pivot. So I take the pivot. In this case, what I do, I select the first element as a pivot. So therefore I do index equal to 0. So I take the first element as pivot. I take index I, let's say I keep it to 0, and so I then do a for loop. So for j equal to 1 to the last element minus 1, I check x of j plus 1 is less than pivot or not. So that basically means is that any element that is less than pivot, I I have assume know that I have to keep it on the left hand side of the array. Any element that is greater, I have to keep it in the right hand side of the array. So if xj plus 1 is less than pivot, that means if the element compare, I just compare the pivot with the next element in the list. So basically, uh, at j, I compare the next element, j plus 1th element, with the pivot. If that is the case, what I do is uh, I sort of swap the elements. So if the next element is less than pivot, I swap the elements. So xj plus 1, xi plus 1 and xj plus 1 are swapped, and xi plus 1 value is swapped with xj plus 1. So basically, this is another way of saying that xj plus 1 gets the value of xi plus 1, and xi plus 1 gets the value of xj plus 1. So there's a Python way of swapping elements. So you can always use this thing. So if I give you an example, x comma y is equal to 2 comma 3. So basically value of x is equal to 2, value of y is equal to 3. Now what I do is x comma y is equal to y comma x. Basically means value of x becomes y and value of y becomes x. So in this case, x becomes 3 now and y becomes 2. So I'm just swapping the elements. Initially here was x equal to 2 and y equal to 3. I'm now swapping it to swapping the value. So what I'm doing here is that I equal to was 0, and I swap j plus 1 and the pivots next element and so on, and then I equal to plus 1. So basically I'm incrementing the value of I also, and then I again do a last operation, which is swap the pivot with the element at index 1. Basically this is the operation of the last position. X0 becomes xi becomes x0. So I swap the pivot with the element at index I, and then I get two subarrays. One is the first part, one is the second part. So I do recursively call the quicksort function on the first part of the list, and I again recursively call the quicksort function on the second part of the list. And once I do all of these things, I finally get the final sort of listing. So if I just run this code, so Python um, and if you see here, it's initially it was I think I have to fill in the this. So this is, let's say, original list is this. The original list is this thing, and then I print the after quick sort. What happens? I print it to sorted. This is quick sort. So if I just run it, if you see, original list was 54, 26, 93, 17, so on. After sorting, what I'm getting is 17, 20, 26, 31, 44, and so on. This is a sorted list after quick sort. So, and here I'm taking keyboard as the first element. So, that's the sort of overall coding structure of Quicksort. Some of the possible questions you can get here in terms of programming examples with Quicksort is that one can be, let's say, some examples can be like, let's say you're given some question in the exam like this. So let's say after um, so let's say after uh, so when some question can be like when the value of j is at j is at, let's say, len of x by 2, then what is the value of what is the value of value of x of j plus 1. So basically, I'm running a for loop here where j is going from 0 to the last element, the pair, last but one element. Basically, that means is the uh, second to last element in the list. When I do this, and if my value of j is at len of x by 2, basically that means exactly at the middle portion, then what is the value of xj plus 1? So in this case, you can you need to go through the for loop, analyze the code in terms of without running the code actually, but analyze the code. Let's say at value j, if it's less than pivot, then I record the value at xi plus 1, and I record the value of xj plus 1, and uh, initially it starts with j equal to 0. So at j equal to 0, I see if x of 1 is less than pivot. So pivot is initially set to x of 0. So in this case, pivot is 54, and x of I plus 1 is basically 26. So 26 is less than 54, obviously. So this thing, the if condition passes and this thing holds. So x of j plus 1 basically means x of this 26 value gets the value of x of I plus 1, right? So x of I plus 1 is basically again I equal to a 0. So in this case, I my I is, this is xj plus 1 is basically equal to x of I plus 1, which is equal to 26 itself, and x of I plus 1 is again equal to x of j plus 1, which is again the same thing, because both of them point to the same element 26. So now I do I equal to plus equal to 1. Basically, I implement the element to I equal to 1. Now I go also in the loop also I do j equal to 1 now. So j equal to 1, you have 26. No? J plus 1, I have 93. And I see if 93 is less than pivot. So 93 is not less than pivot. So the if condition doesn't hold anymore, I again increment j only here, and j is now at 17 now. Sorry, j was 26 initially. J is now at 93 now, and now j plus 1 is at 17, and 17 is obviously less than 54. And again, I do the same things. I was set to 26. So I plus 1 is 93 now. And so you can think of this thing and solve this problem. So you have to sort of deeply analyze the code, how the if condition is working and all. And some of the problems can be like this in the actual exam. You can also run code and see, but I think some of the problems probably won't allow you. So these are some of the questions you can think of. Yeah, so any doubts here in the algorithm? If you have, you feel free to ask now. Now it's a good time if you have any doubts or questions. Um, okay, I think then we'll probably move to more short if you don't have any questions. So, so basically, two, three flavors of problems would be you can think of. One is like worst case complexity. You might be asked like, what is the worst case complexity of quicksort? What is the best case complexity of quicksort? When does quicksort happen? When does worst case happens? When does best case happens? So again, worst case happens when your entire element array is sorted and you take pivot as the first element, and best case happens when you take the middle portion of the array as pivot, and so on. So these are like your sort of possible questions that you can think of. And then also in the code, also you might be given a code snippet, and you might be asked like simple questions like, let's say you have this array as a example, and it might be that some portion of the code is not given to you. Let's say the swap portion of the code is not given to you, or let's say things like this shared, like for example, dash dash this and even dash dash this. So you need to fill in the blank here. So what variables should be here and what variables should be here. So this is the type of questions you need to think of and discuss. So So can you explain the second line why we are using len? Yeah, sure. So so this is the base case that I'm using. So basically, why we need base case? Because in recursion we are doing recursion here, right? So in recursion we are dividing the element into array into two portions, right subarray and left subarray. So left subarray is basically x of list of all elements up to I, and right subarray is list of elements up from I plus 1 to the end of array. So this is a way of indicating in list in the indices. And we are again doing the same thing on quicksort on the first I elements, and again repeated recursively doing it for again for those I elements and so on. So at some point, what I would happen is that I would only get back a array of only one single element or empty list. So in those settings, I'm adding a base case like this. Len of x is equal to 1. Basically, that means is that my element uh, has only one element, which is this condition, or I have len of x equal to 0. That means my list is actually empty. So there is no element in the list at all. If either of these two cases hold, I just return my value x, which is basically the list itself. So if my list has, let's say, only the element 26 only, so I'll return 26 only. If my list has no elements like this, let's say, it's an empty list, I return 0. I return just the empty list itself. The x is the empty list. So you need the base case condition because when you break down the array recursively, at some point you reach a condition where you either have one single element in the array or you have empty element in the array because you are constantly dividing the array into two portions, right? So each of the sub halves is again divided into two sub halves. Those sub halves are again divided into again two sub halves and so on. So at some point you would actually have no element in one of the halves or maybe one single element in the half which you can't divide anymore. So all these algorithms like quicksort and all fall under the case of divide and conquer algorithms. So if you have heard the term, basically that means is you're dividing the problem into different small problems, sub problems, and you're conquering each of them. So in this case, we are dividing the entire array element into two subparts, first part, second part, and we are conquering each of the subparts using quicksort separately on each of them. So that's why I need the base case, which is this question. I hope that answers your query. I think Shreya had asked this question. Okay, so can you explain this case by taking a median value? Okay, sure. You probably would need to compute the median first because your array is not in a sorted array that is given to you. So you need to find some way to actually get to the median. Let's say for the time being, you have access. You know like what is the median on the original unsorted array like this. So median is basically is the middlemost element in the sorted array position. So if I just print the sorted array, which is this, the median I think would be I think 17, 20, 26, 31. So 44 is my median value. So if I pick 44 as the median value and I pivot it, so all the elements less than 44 would be on the left hand side. So 26, 17, 31, and 20 would be on my left hand side. 55, 77, 54, and 93 would be on my right hand side. So this is my first partition that I'm having. Among 26, 20, 17, 31, and 20, um, so there my median would be the mean of 26 and 20 because there are even number of elements in the array now. So it would be average of 26 and 20, and I take the elements that are less than that on the left hand side, and all the elements that the right side to that as the right portion, and so on. I do it recursively, and you can get the same. But you have to make an assumption that you know the pivot at each step, because obviously there are multiple ways to get to know the pivot without doing an entire sorting kind of thing. So I think if you are into competitive programming and sort of you already know about like standard problems in interviews also that people ask is like given an uncertain array, you need to provide the median in the thing without needing to sort it. So there are many ways to do this. You can do something like comparison kind of thing. Also, like if you know bubble sort, let's say, I think I'm not discussing that here now, but one pass forward pass of one pass of bubble sort also in some way you can also get to know the median also. So multiple ways to do that, but for the time being, just assume that you already know the figure. So you already know the median for each one. So okay, okay. I think more or less, I think quick start is result. I think we discussed some of the potential problems that can be asked. I think there is one question. I think. Yeah. So discuss some problems on what you can expect in exams. So for example, as I mentioned, like some examples like you are given fill in the blanks kind of question where you have to fill in the variables in the for loop, let's say. And this is one example. Another example can be like in the code you can have something like let's say um, I'm not thinking of any uh, um, um, okay, so I think there is some questions. I'm just coming to the questions. So I'm just finishing this last few questions of Quicksort, I think, and then I will come to the questions. So yeah, so some of the questions can be framed like this. Again, analysis wise, you can also think of some questions that may be asked, like things like let's say my array is in all descending order, let's say, which is some way like your original input array is in descending order. Basically, you start with 93, then go to 77, and so on. In that case, if you take pivot as the median value, what is the worst case complexity? Let's say if, that is one question. Another question can be like, what is the value of xj plus 1 at some particular acquisition in the algorithm? Or it can be like this first part, let's say, uh, you get after quick sort. Let's say your question can be like fill in the blank of quick sort this first part index at, let's say, um, uh, first element index, let's say. What is the value of that? So it can be fill in the blanks from it. So all this requires you to sort of understand the code or the algorithm a bit deeply. So I also suggest you to highly practice such problems. Like you can pick this code up and you can break it into different parts, analyze it from different perspectives, and I think this should give you an overall kind of understanding. And if you analyze deeply one particular sorting algorithm, other sorting algorithms are very easy to follow. I think just that there are many similarities you can find, so you can easily one doing very well on one sorting algorithm can give you a huge advantage into understanding the other things and solving exam problems there also. So I think with that we are ending with quick sort. We can go to much sort, but before there are some questions. So okay, so I think Divya had a question. So some queries about NOC exam. So yeah, feel free to share like what queries you have. We can discuss them now. Yeah. So while the question is being asked, I'll just go to the slide for Mozart and we'll discuss from there. So yeah. So while the question is getting posted, I'll maybe briefly give you an intro of Mozart and then we'll go into again the code same thing that how we did for Pixar. So again, the Mozart is like a divide and conquer problem, similar to Quicksort only. So given n elements, you sort elements into non-decreasing order, same thing that you want to do. So what is the divide and conquer? If n equal to 1, basically the base case, I terminate. That means every one element in the list is already sorted. If n is greater than 1, obviously that means I have more than one element. I partition the elements into two or more sub collections. I sort each of them and combine them into a sorted single sorted list. And again, I'm doing partition here. So I think that is what is important. In quicksort, we also need partition, which is relevant for us. So partitioning, what is the choice that I can take? So first, n minus one elements, let's say I partition into set A, and last element I partition into set B. And I sort A using this partition scheme recursively, and B is already sorted because B has only one single element. I then combine A and B together. Let's say I have a insert as a function to combine them, and this gives me a recursive kind of thing. I'm doing recursion and all. Okay, so I think the question is posted. So let's discuss the question first. I will come back to the partition thing. Um, Okay, I think this is separate. Okay, Divya, I think we should talk directly to the PMRF coordinator. I think for this course, I think that should help you get some more information about the thing, about the exam. If you are unable to attend the exam, I hope you're doing okay health-wise now. But I would highly suggest you to mail the course coordinator for this, and give share those details with them so that they can help you. Actually, I'm not exactly sure what, because I don't have the correct person's contact. I think you should find it in the course web page itself. Directly contact them and directly write mail to them. I think that should resolve your. Thanks again for posting. Um, okay, yeah. So please write an email, as I mentioned, to write an email to the course coordinator. I think you with the current problem of with the description, problem description, I think they would happily help out. Okay, coming back. So you're combining A and B using the method insert. And as I was saying, this leads to a recursive version of insertion sort. So um, um, so I'm taking the first element n minus one elements into set A, last element as set B, and again I'm not sorting on set A and so on. So the number of comparisons here comes up to be n square. Base case scenario is when my array is already sorted. Then my base case is n minus one, but in worst case, if my array is, let's say, in sort of descending order, let's say, then my workspace is n of n minus 1 by 2, and it's easy to see what is why this is the case. It's basically 1 plus 2 plus 3 plus n. So the number of sort of comparisons is basically comes out to be sum of the first n integers. So in worst case, it would be n into n minus 1 by 2. Um, sharing the screen. Okay. So just sharing the screen answer. I think, so this is my choice one. There are other choices also. For example, you put the element with the largest key in the remaining elements in A. So I'm not going to define choices. I'm just choice one is something that is worst case, base case complexity analysis that we might get asked in the exam. So choice one is something that we can think of. So again, so this is a recursion tree that I was discussing. So there's just a diagrammatic representation. So let's say 10, 4, 6, 3, 8, 2, 5, 7 is your original array, and you partition it into two parts, 10, 4, 6, 3 and 8, 2, 5, 7, and 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 we again do partition 10, 4, 6, 3 into two parts, 10, 4 and 6, 3, 8, 2, 5, 7 into two parts, 8, 2 and 5, 7, and so on. So in Quickstart also I discuss about partition and recursion field. So you can think of that in this mode sort setting also. And in the only difference is that in merge sort, in quicksort you had to do a pivot element and then push all the elements less than that to the right hand side and so on. Here you just partition them. You don't need to sort of push elements that are less than that to that side and so on. So when you partition that, you get the last portion is 10, 4, 6, 3. Basically, elements in the array, each array has of size 2. And then you again divide that into size 1 element array. 4 is one array, 10 is one array, and so on. And there you do the sorting operation. So 4, 10 is sorted, 3, 6 is sorted, 2, 8 is sorted, 5, 7 is sorted. And then when you combine 4, 10, 3, 6 together, you do merge sort. So basically it becomes 3, 4, 6, 10. So basically that's your merge operation. So from 4, 10 you merge it to 4, 10. From 3, 6 you merge it to 3, 6. 4, 10, 3, 6 you merge it to get 3, 4, 6, 10. 2, 8 you merge it to get 2, 8. 5, 7 you merge it to get 5, 7. 2, 8, 5, 7 you get merge it to get 2, 5, 7, 8. And the final subarrays that you get, you again merge them to get the final output sorted list, which is 2, 3, 4, 5, 6, 7, 8, 10. So there's like a merge sort algorithm sort of pseudocode sort of. Basically, it's in C++ in some sense, but in Java, I think. But so I'll just go briefly over the thing. So basically, it's understandable. You take the middle element, left. So you have two indices, left equal to 0, right equal to the index of the last element. You take middle of the mid portion of the subarray, which is left plus right by 2, which is the midpoint. You merge sort a comma left comma mid, and you merge sort from a mid plus 1 comma right. So basically, this thing basically means that your left subarray's index starts from index left and ends at midpoint, and right subarray starts at midpoint plus 1 and ends at the end of the list, right? And you do the merge operation and so on. And so complexity wise, basically what I'm doing is that I'm taking n by 2 subarrays on two sides. So if you see 2 of n by 2 plus the number of comparisons, it's some constant into n, and you can see it, you can do this recursively and solve this problem, and it turns out to be the complexity as order of n level. So again, not going into too much details, but I think if you already know this analysis, how to do this, I think it's quite easy to understand. So that's your Mozart algorithm. So any questions in the analysis part itself, like, yeah, feel free to ask. Okay. Okay. So now I'm sharing a code snippet of Mozart. I would like you to observe that very closely so that if you have any questions, we can discuss them. And I will also run the code in some time. But first, I would like you to observe the code a bit if you are able to understand, if you have any doubts on it. So they can take a 5 minutes kind of, not a break, but I will just say just to stare at the code and get any sort of high level doubts if you have. You can ask them in the chat. Sort of, you can discuss them. Um, like, feel free to do that. Okay, I think you probably have gone through the code now. I think we will then briefly discuss the code and also any questions you have on that. Thing. Any questions on the code? As you have already gone through, any questions you have on the code? Feel free to ask them. Answer. Okay. So we'll discuss the Mozart thing then, in VS Code. Um, we will share my screen. So now I'm writing a Mozart code now. So I hope you are able to see. I just first run the code to get. Okay, so the original list was this thing, and now I get a sorted list of this thing. So remember, this list has number of repeated elements also. So we get repeated numbers like 2, 2, 3, 3, 5, 5, and so on because in the original list there is also repeated numbers also. Okay, so let's discuss the problem ones, like the code ones. So there is a function definition for Mozart, and basically I define a function like this: def keyword, and then my function name, and then an argument which is a list here. Again, I take a base case, which is this thing. It's my base case. If my input list of is less than equal to one, I just return this input list. So there is again another same condition as the last condition, last time condition we saw. Either it has one element or zero element, and this is the same as this thing. So I just return the input list. Else, I take the midpoint as the middle element. So len of input list by 2 is my midpoint. I take a left sublist, right sublist, which is merge sort of input list up till the midpoint. So I do a recursive call to on the left sublist. I do a recursive call on the right sublist, and this is my midpoint that I am finding on the list. And I do merge list. The merge list is basically this operation which I was showing you here. The port 10 is merged to port 10, 36 is merged to 36, port 10, 36 is merged to 3462. So this is my merge list function. So I'm going to merge list function. I'm defining this function. So there is a again a function definition. This function to merge to sorted list. So arguments are and arguments are left sublist and right sublist. Ij equal to I take two variables ij, initialize the index of the left and the right sublist. This is my final result list. I initialize it to an empty list. I iterate through both the left and the sublist like this. I is less than equal to len of sublist, left sublist, and j is less than equal to len of right sublist. If the left sublist value is less than equal to the right sublist value, I just do a simple append operation. Basically, in my example here, port 10, 4 and 10, 4 and 4 is less than 10, so I just do port 10 as an append operation. So that is the thing. Else, if the right value is lower than the left value, then I append it to the list of the right element. So I do result of append to right list j. and I increment j plus equal to 1, and I do this repetitively, and I contribute the rest of the left and the sublist. So this basically is append the rest of the left sublist, and this for append the rest of the right sublist, and I finally get the final output result, which is in this example it is port 10 as an example, and then I do same thing for 3 6, and then I do for 3 4 6 10, and then I do 3 5 7, and so on. So this is my Mozart algorithm. Some questions you might get asked here again are something like, let's say, if I take the midpoint instead of the middle element, if I take a 3, let's say, and I take the one third of the uh, as a partition choice. So basically, I'm dividing my element into one third and two third. So left sublist would be one third, right sublist would be of length two third, and I do this repeatedly, then in that case, what is the worst case complexity? What is the not best case complexity? This type of questions you might just get asked in the exam. From a coding perspective, also you might get asked like in this case there is a thing. So then, what is the value of the question can be like um, what is the value of the midpoint of the left sublist um, first index um, element if you take midpoint as list input len of input list by 3, or if you do len of input list by 4, or what is the comparison with that of that by 3 or by 2. So this kind of questions you can think of, and these are mostly what questions you get asked in the exam. So I would highly suggest analyzing them from this perspective. So, okay, so any questions till now? If anyone have any questions, we can take up the questions, and then I think we can solve some few problems on top of this thing, and then we can go ahead for tomorrow's class. Um, so, so I think there is a question from Shreya. I have a doubt in assignment. Yeah, feel free to share that in the chat, or maybe we will speak up if you want. What specific doubt do you have? So, okay, so yeah, this is the question that we share my screen so that everyone can see. Um, so def of h of x. Um, okay, so let us discuss this problem. So def of h of x. Yes, yes. So let me copy paste this problem into my VS Code so that can select. So I think like no questions in Mozart, I guess. I think I can just erase this thing and I can just the problem here. Okay, let me then let's say a bit. Think that it will, um, okay, so the question is, this is my function definition. So just rechecking once more again the correct definition. Yeah. So this is my function. Sorry, this is my function definition of h of x. And my question is, what does h of 27993 return for the following function definition? So what does h of x is actually doing? So I can actually just run the code and see, but let's for the time being try to solve it without running the code and understanding the problem. So h of x is such that d of n initialize it to 1 and 0. So basically that means d is equal to 1 and equal to 0. While d is less than equal to x, I do d equal to d into 3 and then equal to n plus 1. So basically this again means um, d star into 3 and then equal to n plus 1. So initially b was equal to 1 and equal to was to 0, and then it becomes b becomes 3 and it becomes 1, and then again d becomes 9 and becomes 2, again d becomes 27 and becomes 3, and so on like this. So basically I need to find the value of n. N is actually incrementing by only value of 1, while d is actually getting multiplied 3 by 3. This 27993 is my value of x that I'm given. So maximum I can run d is equal to less than equal to 27993, right? So for d maximum equal to 27993, I want to find out how many such increments have happened for n plus 1, n to n plus 1. Because n is initialized to 0, whatever increment by whatever value of 1 I'm adding it to n, that is the final value of n that I get. Because let's say n was initialized to 0 and I do n plus 1 four times, let's say. So basically, first time it becomes n equal to 1, second time n equal to 2, third time n equal to 3, and fourth time n equal to 4. So final value of n would just be equal to 4. So for that reason, whatever number of times this while loop actually runs is actually the number of times, is actually the final value of n that I get. So basically, for this question, I just write, I'm just writing as a hint. So number of times the above loop runs is the answer. So this is my value of n, right? So what I'm getting is that b of I want to find out b of b. Let's say n is the answer. So d. Um, so to find that, what I need to do is d of so d is getting multiplied with 3 and so on. So d to the power 3 of x, let's say. So d into 3 into 3. This thing is getting operated for, let's say, for X number of times. So I think there is a question. Okay. So so d into 3 is happening several times until I get the final value of n here. So I want to see like for how many times d equal to d into 3 happens. So um, this is my this is the thing that I want to find out. So d into 3 to the power of n is equal to x. So I can sorry, I read the wrong thing. That's wrong. So d is multiplied by 3 in each particular iteration that I'm seeing here. So my and so what I need to do is I need to find out 27993. Let's say I do um, log of log of 3 of 2793 is something around 7.85. So why I'm taking log of 27993 to the base 3? Because I'm getting sort of the value. I'm keeping on multiplying d by 3 times every at each iteration until I get to d is equal to 27993. So the number of times I multiply d by 3 is basically the time I get the thing, the value to uh, my final value. So basically 3 to the power n is should be equal to less than equal to x. So not n actually. Let's say z actually is the value that I want to find. 3 to the power z. Let's say d is at 1, and then d becomes 3 and 27, 9, 27, so on. So whatever the value is z, that is the final value. So in this case, I do 3 to the power n because at each iteration I'm incrementing the value of n by 1. So I just need to solve this thing. 3 to the power n is less than equal to x. In my case, x value is actually is equal to 2793. So in this case, n is equal to some of 7 would be my final answer. So I hope that answers your question. I think you can also run this program, I think, to verify. Uh, I think, okay, sorry, the print statement is counted. Print of 8 of 2790. So I think it's another 10, I think. SC, I think I made a calculation mistake. Let me check the log value of this. Log value of this is roughly just 3. Okay, so it's around 9.321. So that's why the final value comes out to be 10. So I made a calculation mistake here. I think it's around 9.321. Okay. So I hope that answers your question. Um, so there was another question in the chat. I think it was um, um, so which was solve programming questions of week 4. Okay. I think we have a few minutes left. We can solve this, and then I think we can discuss the remaining part tomorrow once more. So can anyone share? I think I have access to the assignments only. Can anyone share the programming? I guess this is okay. So let me open the assignment sheet itself. Week 4 assignment 1 is the first column. I think one of the people has a question on this. So the mystery L is a empty list. It should return the list itself. Else it should return the following. Okay. So what does this thing return? Uh, so this is basically a list question, I think, like not any algorithm sort of question. So what does this thing mean actually? Basically, you just need to know these things and this thing. I think that should actually help you understand. So what does this thing? So let me actually show you by examples. I think this should help. So let's say I have a list of numbers, say 5, 4, 10, and I print say L of 1, 0. What do you expect it to return? It should return me the last element only because I'm minus 1 basically means so it starts at index 0, right? So minus 1 actually goes back to the last thing. You can think of a circular kind of loop kind of thing. So 0, 1, 2, 3, and then again from 0, if I go backwards, it's minus 1. So it's basically 3 itself, the index 3 itself. So this, and from index 3, starting at index 3, I want to go to the end of the array. So that's why this returns to 10. So that is one thing. And then if I go back to the column once more, this portion, which is this thing. So what do you again think this should return? It should return the entire element itself, entire list itself. If I just do this thing, now starting from 0 index, I want to go to the last element index, which is 10, minus 1 in this case. So it should go to give me just 459 because it's not. If I do this one, it should give me the entire list. Sorry. If I just do this, it should give me the entire list. 4, 5, 9, 10. But if I give a minus 1, I just get to that position, but I don't include the last element. So I get 4 by 1. So save that and I get 4, 5, 1. So in this example, in the question here, it says that mystery of 31, 32, 71, 18, 51. So it first it goes to the else condition, L of -1 up till last. That means 51 is my first element. 51 is this thing, and mystery of L of this element up till this thing. So mystery of this thing, the first subpart of the thing, 31 to 18. So 51, and then I do what I do is I do 18. I again do 31. So basically, it gives me in a descending order thing. So basically, my list is getting reversed in some sense. So 50, I started with 51. I get 51 here. So this thing again is a recursion problem. So I again call the same function again, and this thing returns me 18 plus 31, 32, 71. On this again I do mystery. I get 71, and then I again do 31 and 32. I get 32, and then I just get 31, and for 31 I just get this thing as so 31 as is my final list that I get, and so this gives me 31 only, but this part gives me uh, an empty list. An empty list is basically I'm just returning that list itself. So basically what is happening is just I'm reversing that in a descending order. So 51, 18, 71, 32, 31. That's my um, reverse list that I'm getting. I hope that answers your question. Okay. I guess that's the. Uh, I guess there are no other questions then. Then I guess we can briefly discuss tuples. I think the dictionary and tuples. So I think with that we should end the call, and then we can discuss it tomorrow once more. So basically, like Python tuples. How do we define tuples? So basically, tuple is like a collection of lists of Python objects. The sequence of values stored in a tuple can be of any type, and they can be indexed by integers also. And the important difference between a list and a tuple is that the tuples are immutable. So basically, you can't change the values in that sense. The tuples are defined by specific items separated by commas with an optional pair of parentheses. Tuples usually are used in cases where uh, statement or a user-defined function is used. So if I show you some examples, so um, uh, so I create an empty tuple by following this. So my tuple is this thing. I then do, let's say, a tuple having integers, let's say, which is like this. So similar to list only. So um, uh, I can have tuple with mixed data types, this different structures like this. So the first data type is of type integer, then it's type string, and then it's of type float. I think there is a question. I think. Okay. I'll just go to that question in a bit more time. So this is basically my tuple definition, sort of what I'm saying. So I can also have a nested tuple also. So something like my first data type is of type string, and then I have a list, and then I have again a tuple. So this is a nested example of a tuple. So likewise, you can define different types, and a tuple can also be created without using any parentheses. There is something called as tuple packing. So I can have something like this also without the parentheses. You can also define it like that. Tuple unpacking is also possible, which is something like this. ABC is equal to my tuple, let's say. So my tuple was, let's say, set to 3, 4.6 and dog. So value of A would be 3, value of B would be 4.6, and C would be the string dog, and so on. So those are the things I think are mostly the examples of tuples. I go to dictionary now, and in dictionary, what I have is a key and a value thing. So value can be like, let's say, some number, and some string can be a value or anything else. So some examples can be like, let's say, like this. So key is one, values to study the characteristics of DC generator, and like this. So different examples have created an entire dictionary of sort of different um, of 29 keys and different values, as you can see here. Now, if I want to sort of get the value of, of let's say, at value key value 2, let's say, then if I just want to print that, I can just directly access it and sort of print that to study the characteristics of a DC model. This is my key value at 2. So key dictionaries are actually useful in many data structures, as you will see in upcoming lectures also, and different algorithms you encounter later on. So these are some of the examples. So here's my output, sort of any sort of like high level questions here. Like, feel free to let me know. So basically, this dictionary NPTEL EX2 actually contains the experiment number as the key and the experiment name as a value, and we can access the value corresponding to a key by using the key in square brackets. In this case, we are accessing the experiment name corresponding to experiment number 2 in the above example, and it should be just be the characteristics of DC model as a value. In this way, dictionaries can be used to store and retrieve data in Python. So that's the main idea. Yeah. Okay, so I'll just go back to the last question of today. I think then we'll go to tomorrow session, which is again from 3 to 5, and then I think we can discuss more. So, okay, so any question? Okay, so I need to explain this. Okay, so there is a code for insertion sort. Uh, so the thing is that what you're doing is like you are taking a for loop for the entire sequence of array, and you are doing this for loop is going from 0 to then of sequence of -1. Let's say the total array element is n, so you go from 0 to n-1. You take the position of the for loop index while position is greater than 0 and sequence of position is less than equal to sequence of position 1 -1. So this the AND condition basically means that the array at element at the current position is less than equal to the element of the array at the previous position. If it's the case like that, then you have to do is that basically means that your array is not in a sorted position, because it should be in a increasing comparison order, but it's not. So that's the reason why it's you have to swap the elements. So what you're doing here is a swapping operation that you're doing. So I hope that answers your query. So why pause equal to slicing? So because you are you want to do it at each position, right? And you want to see at each position for that whether the current element at position this thing is less than equal to the current element at the previous position. And so that for that reason, I'm assigning it to slicing. Okay, I think we are mostly upon time. So let's discuss the remaining questions. So I think for week 4, I think we are mostly covered week 4 everything. I think we probably have list comprehension left. I think we can discuss that tomorrow. And week 5 is as usual from tomorrow. So yeah, with that I think we should end the call today here. Thanks again for joining today. And you should also join tomorrow same time 3 to 5, and we will discuss assignments and tomorrow. Thanks.